So good morning, everybody. I'm Dr. Pratap Singh. I'm the session lead for this session, this community session, which is systems approach to flood forecasting. As we know that there are so many components of in the flood forecasting model, as well as the application. So that's why we have written it like putting the pieces together. So I'm working as a water sources expert and as a VP in the RMSI. And I will be leading the session, and Mr. Lakshman will be working as the session manager. And the schedule, if you see, I will be giving some introduction about the topic. Then we have our panel experts. They will be talking in brief about the major challenges, major opportunities, major issues related to flood forecasting in their specific domain. Yeah, next please. Yeah. Lakshman, next slide. Yeah, if I tell you about the flood, about 39% of the events of the disasters are occurring in the form of the floods. So that is the reason that we have selected this topic because this is a very important, challenging disaster events globally now. Next, please. So broadly, essential component for the flood forecasting system, which we have decided to deliberate to discuss include is the collection, transmission of and utilization of the real-time data for the flood forecasting models, type of the models to be used in the modeling, how we can make this information understandable to the relevant stakeholders, what are the best and effective way, reliable way to communicate the outputs of the model to the community, and how quickly the community can or the agency can respond for the preparedness. So these are the topics for our deliberation, our discussions related to the flood forecasting system. Next, please. Yeah, now we are starting our debate, our discussions on the different topics relevant to the flood forecasting. So the first important component for the flood forecasting is the collection, transmission, and the utilization of the real-time meteorological data for the flood forecasting. We have two panel experts, Dr. K.J. Ramesh and Mr. Prakash Yadav. Both experts were working for the India Meteorological Department. They have a long experience of working in the meteorology. K.J. Ramesh was the former director of the IMD. Prakash is right now heading the hydrology department. And they have a lot of experience of working all kind of the instrumentation, data acquisition, operational flood forecasting. So we hope that they will be giving their opinions about this topic. So Mr. Yadav, you can start your presentation now, please.
Unmute your mic. Yadav, you have to unmute your mic.
Okay, sorry, sir. Good morning again, and thanks, Dr. Pratap, for a nice introduction. Today, myself will be talking about the collection, transmission, and utilization of the real-time data for flood forecasting. As we all know, that for an accurate flood forecasting, you need accurate meteorological forecast, particularly rainfall forecast. And for an accurate rainfall forecast, you need high quality, high density, real-time meteorological data. Next, please. This is although India has thousands of network of rain gauges, but I have just produced here the network which is dedicated, installed, maintained, and the data collection is being done as per WMO standards. This station or gauges are about 5,000 in the country, and we get the data on real-time basis and produce the different rainfall products over different temporal and spatial domains on a daily basis, and these are being used for you can say information about how much rainfall is occurring on a particular city or a district in a real-time mode, and that gives good information for the flood forecasting people. Next, please. Yes, of course, for an accurate forecasting system through numerical modeling, the basic information, the basic requirement is the initial value, which depends upon the real-time data. And data not only from surface observations, but also from remote observations, satellite, radar, ship observations. All those data should be available in real-time mode. And this has to be integrated and through running different high-power computing systems in different numerical models of different resolutions from meso-scale model to global models are being run, and then the end products are being prepared for the users. And here the product is the rainfall forecast, which we provide to the hydrological people for issuing the flood forecast. So this is the system of forecasting, and for which the data is very much important. Next, please. But there, when we talk of the real-time data, there are a few challenges. Of course, as I said in the beginning, the accurate rainfall data and forecast is the key for the flood forecasting. But there are some challenges, and one of the such challenges is that we use different type of gauges. We all know the rainfall data is collected from rain gauges, which have different measuring mechanisms: accumulation gauges, tipping gauges, weighing gauges, optical gauges. So there are some errors in different measuring mechanisms. Of course, there are some problem in calibration and precision errors are also there. Even some errors have come from wind and evaporation, even site location. If the equipment or gauge is not being installed with good exposure conditions as per WM standards, there can be some error. So this is one challenge. Another is the different sampling rates. And here I mean that we take synoptic observations 3-hourly and automatic weather station observations hourly, but radars are available at 12 to 15-minute interval, satellite rainfall estimated available at 1-hour interval. So there are different sampling rates, and we have to have some mechanism to integrate all this data into our modeling process. Density of network, particularly rainfall network, is very important, and it is almost always found inadequate for a properly to understand properly the variability in the rainfall over the different river basins. And as we know, the rainfall has a high variability, and therefore we need more density of the gauges over different you can say areas. And but there had to have some guidelines. What type of density is required for different type of flood forecasting, whether it is plain river for flood forecasting, whether it is fleshy river flood forecasting, will have different type of density requirement than that of the urban flooding and flash flooding. So we have to have some standard guidelines for density of network for forecasting of flood for different type. And of course, we all know that radar and satellite-based microwave and infrared observations, they provide very useful data on spatial distribution of the rainfall particularly, but they are to be calibrated and validated with the ground observations. And again, we have to come back to those surface observations of high quality, which has to be used for their validation. Next, please. So what is the solution and the way forward? One solution is that we have to go IoT-based sensors because we understand that the real-time access to the raw data, raw meteorological data, raw rainfall data is a fundamental step for providing real-time access to the meteorological information. So we have to shift from conventional observations to automatic weather stations, and now IoT-based sensors, because we can define rules to trigger alarms for the efficient early warning system at the sensor level itself, which are IP-based. So IoT-based sensors are required for an effective early warning system. We have to have a lot of investment with regard to tend manpower and resources for maintenance, because quality of the data is very, very important when we come to the for forecasting.
Yeah, Mr. Yadav, thank you very much for very important and vital information for the data collection. May I request Mr. KJ Ramesh now, who has long experience working in the meteorological department related to floods and the instrumentation, just give his quick overview of this issue.
Yeah, thank you so much, Chair, Dr. Pratap Singh. Good morning to colleagues. Data heterogeneity, as it was pointed out, is the key and the reality which we have to learn to deal with in generating a merged data set of a most representative nature with quality assured and quality controlled data at a catchment scale to assess the hydrological response of a river basin to a high intensity rainfall event happening in subcatchments intermittently. So we have to have a merged data set of conventional observations that was told just now, and the satellite derived estimates, radar derived estimates, and we have to merge and generate the most representative and a fine resolution, fine scale, at least 1 kilometer to 3 kilometer grid scale rainfall data, and the temperature data is also required for the hydrological assessment from the meteorological observations and the satellite derived observations. Added to
So you are suggesting that the data, the rainfall data or the weather data from the all sources, whether it is
yes,
on space, should be compiled and
and
processed
merge
and
it together, and the representative data set got to be prepared in for three kinds of hydrological assessments. One is the river hydrology, second one is the urban hydrology, and the third one is the coastal hydrology, where storm surge related inundation and rainfall taking place in the coastal area, coastal inundation. We have three different kinds of applications. The data got to be generated, and the frameworks are different: hydrological assessments and the response of a rainfall event. So that's where the apart from this, forecasts generated by the models are also used to assess the possible future rainfall hydrological response of the basin to 24 hours later, 48 hours later, 72 hours later. It is a joint mandate.
I think yes. Yes, thank you, Dr. Ramesh. I think we will be talking, interacting further, because
okay. Thank you. Thank you.
So we move forward because of our time limitation. Now we are going to the next theme, which is the data for the situational awareness. Very recent topic, and we have two panel experts, Mr. Michael, who is the GIS specialist for the World Food Program, and Rohini Swaminathan. Again, she is emergency expert, emergency analyst for the UN. Both experts are associated with the United Nations Development Program and working on space applications for the floodplain mapping. It's huge for the public in the real sense. So thanks to both of you to join for this panel, and now you can share your views, your presentation to the audience, please.
Thank you, Mr. Pratap. If I may ask to go to the next slide. It's a pleasure to be part of this panel and provide from a humanitarian perspective on how space applications is used, not just in flood forecasting, which would be the core of what we will talk about today, but also in the wider disaster management cycle itself. As you can see in the slide, space applications really play an effective role, and we have gotten to a point where we need them. It's a necessity. It's not a sophistication anymore as it used to be even a decade or two ago. We predominantly use them in the risk and vulnerability analysis, in mitigation and preparedness, because we believe that's the core to save as many lives as we could. We rely a lot on modeling impact, but until very recently, we didn't have a global flood forecasting option available. It was available at a country level with few meteorological departments here and there, and only very recently we were able to get this and integrate this within our decision-making system. Not just in mitigation and preparedness, when we go to response, we all know how crucial space applications are. From satellites to unmanned aerial vehicles, we have been adopting all the recent technologies to effectively respond to any major floods across the world. And we don't stop there. We go all the way into recovery. Even if the flood lasts for a month or more, we still model, use the flood forecasting information to enable aid delivery around. If you could go to the next slide. Just to give you a quick example of how it was even a couple of years ago, our preparedness boils down to a map like this, where we rely heavily on modeled flood impact layer. And this shows with different return periods, and it was globally available after Global Assessment Report of 2013. But this does not give the entire picture. We could use this information, but we didn't know when the flood would happen. And obviously not all the rivers in a country would get flooded. So we didn't have any flood forecasting information. But our preparedness was limited to these flood hazard zone models and dependent heavily on estimating approximately the population living within this zone. If you could go to the next one. And at UNICEF today, we are relying more and more on integrating different inputs from different sources to be able to do an effective early warning. And as you can see here, the red, yellow areas are coming from a Group on Earth Observation initiative called Global Water Sustainability Project. And this project now integrates all the different models and provide forecasting information with a 6-day lead time, which is wonderful in terms of early warning and preparedness. So now we have at a community level, at a specific watershed, which river could get flooded. And we combine this with the modeled hazard, because having the information of a river, a forecast information is not just enough. We need to answer the next question, so what? And we calculate the people around that area who might be living in flood hazard to go for preparedness plans. And we combine this with qualitative analysis. Oftentimes, quantitative data alone is not enough to get the whole picture. And we provide the context to our communities, to our country offices. But here I would like to call upon my colleague, Michael from the World Food Program, to give specific examples on how spatial applications are used there. Over to you, Michael.
Thanks, Rohini. So basically at WFP, what we're trying to do is to develop this automated disaster analysis and mapping. And one particular example is for floods. And if you can go to the next slide. So basically what we're trying to do is to provide automated systems that delivers these types of products in a nice map, like a dashboard, a report, and initial impact assessment, like the table you see with some colors there. It's basically saying which country and which district will be affected by flooding. And then we do this in a systematic manner by sending it to the country offices in an event of flooding. But particularly for forecast, if you can go to the next slide, we are trying to do an automated system as well to send them to send these people a map or a dashboard of the potential flooding using a data from a global one, which is not very good because it only works for large river basins like 10,000 square kilometers an area, which is from GLOFAS, from the European Commission. But we've also partnered with a UK company that is able to do high resolution flood forecasting. The company is called Fathom. And once we have those data, we will be able to provide flood forecast using a rainfall information from GLOFAS as well. Next slide, please. So basically, we are also doing some flood forecasting for financially for releasing money. For example, for forecast-based financing is what we call. So, but basically what we're trying to do is to get anomalies of rainfall for a particular admin level, and then say if this rainfall will exceed the normal rainfall that they have been receiving historically, then WFP can provide some assistance already in cash so that people can prepare even before the shock happens. So we are doing this as part of a German-funded projects in several countries, but not the entire WFP countries. Next, please. So basically, I will show you also some very high resolution flood mapping that we get data from partners, from very high resolution satellite image providers. We were able to identify impact level analysis in an event of the actual event. Next, please. Now I'm going to show you a particular example that we did using drone data, which is really used for preparedness with the government of Mozambique. Next slide, please. So what we did here was we flew over this Likongo River basin on the downstream and the upstream. So we did some flight missions and covered a sizable amount of area. And what we were able to do, next slide please, is to simulate this flooding on this very particular location. So basically using the discharge and flow velocity, we were able to simulate the maximum flood inundation that happened in 2015, which is our benchmark. Next slide, please. And then what we are able to do is to really identify how many people are living in those exposed locations by using data from OpenStreetMap. Next slide, please. So what we're able to get from that exercise is that we get real-time information from the water managers in that particular river. So for example, if they feed into the system, the water depth, it actually in real time simulates the level of water because we use a vertically correct drone, high resolution RTK drone. So we were able to do this near real time with the correct vertical accuracy. Next slide, please. In that, in summary, we were able to see at particular which event, how many buildings will likely be impacted, and we are actually using that for the preparedness and for the response side for delivering aid. Yeah, I think that's all from my side. Thank you.
Thanks, Michael. Lakshman, could I ask you to click 6 times here to show how we use spatial data in recovery, especially Earth observations, but also combined with secondary data. So this is the week 1 of Cyclone Idai in Mozambique. And as you go through the weeks, you see the flood water receding. But flood forecasting is still important if the rain would be accumulating in certain areas, and we want to focus on areas where we cannot deliver food aid. The colorful lines you see here are the roads where we got information from the truck drivers where it was accessible or not. And if you click one more time, you see that there is massive data gaps around. So we are not able to effectively use from flood forecasting information to the impact information to delivering aid, because obviously there are still a lot of data gaps. If you go to the next slide, quickly touching upon the challenges that we face in effectively using geospatial data, the first thing that comes to my mind is timely availability of processed data. Oftentimes we have these amazing models running around the world, but we are not able to bring that into the hands of the people who need it the most. And more often than not, what happens is we have the forecasting information, but we do not have the impact information, which is the most crucial of all. We have to answer the question, so what if a flood is happening here? How many people, how many vulnerable people are within this region, and what are the damages that could happen to critical infrastructure and how it might affect? And we do not also have a capacity, because geospatial science in general is still a very specialized field that has not been widely spread. And ironically, one of the challenges that we face oftentimes is actually information overload. We have multiple actors doing similar work and giving competing information, which could be contradicting one another. So we still need a lot of work in terms of standards, in terms of partnerships, in terms of funding, and addressing privacy issues that remains largely in the humanitarian space. And it's just our hope that moving forward, we would be able to integrate technical information such as high resolution flood forecasting to saving people and have this seamless structure in place. And with that, thank you so much for having giving us an opportunity to present. We work with a wide variety of partners, and thanks to all the partners, especially the International Charter for Space and Major Disaster, whom we work closely in terms of response. And over to you, Mr. Pradap.
Yeah, Rohini and Michael, thank you very much. Really, the efforts you are making and the latest applications of the, let it be remote sensing, let it be space, you are making for the flood estimation, impact assessment, all kind of the influence. Very useful interaction, very useful information for our theme. Now we start the next one. The next theme is the flood forecasting. We are two persons who will be talking in this. One is myself, Dr. Pratap Singh, and another is Mr. A.B. Panda. A.B. Panda is a very renowned personality in the water sources in India. He had been the chairman of Central Water Commission. Right now, he's Secretary General of the International Commission of Irrigation and Drainage. in which 78 members are the country of the ICED. So today he will be talking on some flood forecasting basic issues, basic problems, basic challenges on the subject. From my presentation, I would like to explain that what is happening these days for the flood forecasting, and what kind of the models are there, what are the limitation of those models are there. So I will be talking in that. So in this slide, which is on the screen just now, you can see that the events of the severe rainfall or the heavy rainfall in India, this is the Indian analysis, but this kind of the analysis we found it well supported globally also. There are incident of such high rain events, increase of the rain events with time, with years globally. Next, please. So coming to the flood forecasting models, every model has inputs and the outputs and the processing modules. So for the flood forecasting, generally the rainfall, real-time rainfall and the forecasted rainfall becomes the very important input to the model. Real-time for the realistic situation for the particular time and day, and the forecasted for the lead time, whatever the lead time we choose, whether it is 2 days, 3 days or 5 days. So we use this in general in India with the support of the India Meteorological Department. We are using the weather WRF forecasted rainfall, which is available on 3 km by 3 km resolution. And we are thankful to IMD to support for the whole country on these issues. The discharge data generally again provided in the Indian context from the Central Water Commission, the state departments, and regarding the other data, that is LU, LC, land use, land cover, DEM is one of the very important parameter if you go the inundation purpose for the modeling. Next, Lakshman. You see, if I quickly brief, what is the workflow for the flood forecasting and the warning systems. Overall workflow is something like, rainfall goes, data goes as the input to the hydrological model. Then we compute the discharge estimate. We estimate the discharges using the hydrological models. And these discharges are used for hydraulic model, which is giving us the inundation grid, velocity grid, and the water surface. There are a number of models present right now globally, like the HECRES is very commonly used. Mike is also there. And there are some other kind of the models for the hydraulic model being used and updated by the developers time to time. Then these models or these methods, you see, the output of the model is published in form of, water depth, extent, and this alert is given through the report, SMS, and the mail. And these days, we are seeing the trend that all the models are web-based models. They run automatically and get the data automatically, run the model automatically, and disseminate the information to the stakeholders. Next, please. So this is this kind of the output one can easily get, using this the latest state of art the models, and these can be verified using the satellite information. I'm showing here the output of one of the models which RMSI is using for a World Bank funded project for one of the river basin in the Uttar Pradesh. That's a tributary of the Ganga River. And you can see that the river basin, sub-basins of the whole river system and the output of in terms of the inundation for the area of interest. These models are prepared by RMSI and with the help of all the experts available in the different sectors. And on the daily basis, such information is provided to the stakeholders. That's very useful information for the application, for the disaster reduction and the society welfare. Next, please. So now this was a brief from me about the modeling aspects. Now I will request Mr. A.B. Panda to discuss, to explain, to deliberate his views on the flood modeling and the forecasting. Mr. Panda.
Thank you, Dr. Pratap Singh. We will go on a real-time basis about what is actually done in a subcontinent country like India. Uh, India is about 40 million hectares of flood-prone area. It's a very large area, especially in our Gangetic and our Brahmaputra plains. We have very large areas which are chronically flood-prone, and every year we have to struggle with them. We have at Central Water Commission, we have flood forecasting services throughout the country, which provides the much needed coordination and timely inputs to individual states for flood management. There are two aspects of the flood as a disaster. One is the forecasting, and then the second is the management. If your forecasting is accurate and if your forecasting is reliable, the managers know really what is to be done and how it is to be done. So from that angle, the flood forecasting services that are provided by Central Water Commission in the interstate rivers context and in many other rivers, it is very much important. Flood forecasting network, it covers 325 stations, covering 197 low-lying areas in cities and towns, and besides 128 reservoirs all over the country. Now, this is something which is very, very important. When we have the inputs in form of rainfall and precipitation, we still need to know that what is the actual flow that is happening in a particular river. And the flow that is happening in a river is not only affected by primarily affected by the rainfall, but is also affected by the various modifications that have happened across the river, like presence of dams, presence of weirs, there are certain encroachments in the channels, and so on and so forth. So it is very much necessary that we need to really provide the information from the point of view of the actual flows that are actually happening. For that, a lot of work has been done. Installation of automated instruments for measurement of water levels are there. But the new challenge that is coming up is flooding in unexpected river reaches. In many of the places now, because of the extreme rainfall events, suddenly we find an area which was actually arid, suddenly facing the floods. And for that, you have to give a very short duration and a very, very timely forecast, because the population there, communities are not really prepared to handle those kind of floods. Another very important issue that is happening, especially in our Himalayan region, is the glacial lake and landslide dam breach events, which are also needing very, very extremely fast responses, especially in the areas of the hilly region where the general geometries are relatively well defined. We have a good set of models through which we can provide this. But then when it comes to the plains area, this issue becomes quite difficult to handle. The frequent changes in floodplains, especially in the urban context, that makes the inundation assessment very, very difficult, because the channel geometries keep on getting modified, and because of that the hydraulics of the channel keep on getting modified, and because of that various inundation which were not expected really comes up, or the disaster management requirements in certain areas which were supposed to be actually the flood holding areas come up very well, and then that is a constraint which we need to work. Unrealistic constraints on reservoir operation. We have got many of our rivers are not really virgin rivers. We have got large number of structures on them, especially in form of dams which are having the storages. And because of the operation of the storages, the response of the river downstream of the reservoir is becoming a different kind of a response, which is having a lot of area of reservoir operation coming into the picture, apart from the rainfalls that are happening. And for that, integrated operation of reservoirs and providing flood cushions in the reservoirs and managing them dynamically, especially in a cascade, is a big challenge that reservoir operators have to face. And you have to provide them with very reliable information about the inflows and outflows in order to make them respond and create a suitable and sustainable environment on the downstream. Coupling with the real-time outflow data from reservoir is a real challenge, especially in the interstate context. There are multiple managers, and each of the manager acts as per his own priorities and as per his own information. And coupling this with the real-time data is a challenge that we need to really handle in a systematic manner. Next, please. So these are the new horizons of developments which the Central Water Commission and various other engineering community across the country are taking up. And that is the extensive use of GIS technologies, with semi-automated image processing, especially for the inundation modeling and for the real-time operations for flood management. The detailed, precise topographic digital elevation models are the need of the hour, where we need to work very hard, because the elevation model is the one which ultimately decides what kind of inundation are likely to occur, which are the facilities which are going to go under, and accordingly how the disaster management will have to respond. Urban flooding is a special phenomena that has come up, and which is primarily a drainage phenomena more than a flooding phenomena in the conventional sense, because the drainages are getting choked, and there are regional the flood modeling for the urban area is becoming a very difficult exercise. But then we need to really work on this in a systematic manner. Leveraging the data transmission and processing through the mobile networks can assist in better collection and intensity. This is an area which has got its pluses and its minuses. In the extreme events, you have got the mobile networks going out of action and you may lose the data. But then on the other side, even if the event is not extreme, but then you have got much more dense networks through which you are able to access the data on a much more reliable fashion. We need to rely on a set of models. It is not possible to really look at one model and then provide the entire country or entire very diverse area into one solution. We need to have model libraries. We need to actually work on the cloud platforms for better and widespread access to the processed information about floods. For example, recently Central Water Commission has now joined with the Google and is providing its information on the Google Maps, where the real-time information can be accessed by the public in general, apart from the other warning areas that are there. There are various other areas like artificial intelligence-based tools for flood modeling. They are also coming up. We need to really prove them so that the processing and the information becomes more realistic. And the leveraging of the massive data collection and data mining technologies are the ones where we need to work very hard. There are a lot of data that is available on the ground. For example, for every reservoir, you have got a data on the downstream about which villages will get submerged if a particular kind of release is made from the reservoir. But then this data is relatively uncoordinated, but then this will have to be dovetailed with various scientific data in order to see that we are able to provide a reliable information about the flood event that is likely to happen. So these are some of the areas which are required
I think Mr. Pandaji, thank you really to highlight these are the real issues. For example, you are telling about the integrated reservoir operations, under the flood scenarios. Such kind of the exercise, the operation is essential, very, very essential. Application of the latest technologies, including artificial intelligence, very good points you are suggesting. I think we will be talking more if the time permits on this issue, but we move on further for the next theme, which is effective communication to the flood warning and the reaching to the last mile. I welcome here our two panelists, Professor Janki Andharia. She is Professor and Dean at Tata Institute of Social Sciences, and she has a experience of the disaster management teaching and the leadership more than 32 years. And she has been, awarded global awards for the disaster management teaching and the leadership. So certainly we are very happy today to have Janki and Dr. KG Ramesh. KG Ramesh already briefed you, former Director General Uday IMD, and right now commissioner member for the technical member for the Commission for the Air Quality. So they are the two experts who will be talking this. Professor Janki.
Thank you very much. And thank you also for having me here. I wish to congratulate the organizers to have social scientists and technocrats and scientists on the same platform, which actually raises critical questions on science, policy, and community interface. It's an old debate, but embedded that we are within our disciplinary trainings and our institutional affiliations, we are where we are with regard to serious challenges of ensuring that science is at the service of society. I would just like to inform the audience that within our master's program in disaster management, we have 3 specializations. It's called Technologies for Disaster Management, Disaster Policy and Action, and Disasters and Development. And our endeavor is to bring about better convergence between scientific advancements and community needs. And I actually appreciate Rohini's honesty and when she mentions gaps, and my presentation emphasizes the community perspective. So why is effective communication of flood warning and reaching the last mile important? What is the significance of the last mile, and what is it that we need to do? I think these are questions that I'm going to try and answer. So on the one hand, clearly we have highly sophisticated early warning systems, models that use expensive technology. And yes, there is also high levels of accuracy. It is indeed a matter of pride for all of us. However, when we look at these models, where are the people and where is the community in, let's say, typical hydrological models? Data suggests that around 85% of the people exposed to different kinds of disasters, whether it's cyclones, floods, droughts, earthquakes, live in developing countries, and more than 69% of all people killed by disasters between 96 and 2015 were classified as receiving a low income, or maybe they belong to the lower middle income categories. This is CRED data as well as UNISDR data. So disasters disproportionately affect those within the lowest socioeconomic status, including those suffering from poverty, as well as maybe minorities, discriminated groups. And in many developing countries, we know that women's low socioeconomic status, which implies unequal access to information, to health, and assets, all of this contributes to a reduced ability of women to cope with disasters. So this has led to gendered inequalities in the death ratios and livelihood losses during natural disasters. So let me sort of remind all of us that there's plenty of data that tells us that we are missing the most vulnerable repeatedly. And somehow our sort of scientific community tends to overlook this, perhaps feeling that it's really not one's own problem. The problem lies somewhere else. It's a policy issue, it's a governmental issue, but I think these are global challenges and we need to sort of overlay one on the other. So when we speak of the last mile, we are referring to the most vulnerable, living in precarious conditions, and from the perspective of early warning systems, those who are most unlikely to receive early warnings. So I think that's the group that we are sort of bringing to the fore. And when we speak of disaster risk reduction, which is our sort of collective aim, early warning systems indeed constitutes a major pillar. I don't need to sort of remind ourselves what is the EWS. It is an integrated, supposed to be an integrated system, but well, is it really an integrated system is a question that we all need to ask ourselves. And if it's not, what is it that we need to do? What kind of focuses do we need to sort of bring in rather than maybe, I'm raising a little provocative question, rather than keep talking about more and more advanced technology, which probably makes us proud to possess it, like artificial intelligence and so on. But we are really, are we able to deliver on the promises that we make? So what's the value frame that we need to kind of embed ourselves in? So the idea of early warning system needs to sort of look at human rights, and government departments, whether it's the Met Department, Irrigation Department, Water Resources, Revenue Department with its entire hierarchy, which goes right down to the village level, all of these must be viewed as duty bearers. Unfortunately, we do not look upon ourselves as duty bearers in a sense, and we miss the community completely. So the goal really is to save lives and property, and having advanced scientific knowledge of impending rainfall or forecasting techniques and models is not enough, is the point I'm making. So this information must reach the last mile in a timely manner with clear guidance for action. So in the words of Ban Ki-moon, yes, we must increase investments in community resilience with full participation of women, young people, and other groups. And can we make things as local as possible, as international as needed? And local action must be driven by local needs and complemented by regional and international support. So what is at center stage is something that we need to really interrogate. Okay, the next slide shows large-scale flooding events. And yes, our aim is to mitigate impact, optimize strategic planning of water resources. Although several developed countries have well-established systems for river monitoring and flood early warning, figures of population affected every year by floods in developing countries are really, really unsettling. It really should sort of make us wonder, is this acceptable to all the scientific community? Okay, because somewhere we tend to place the blame on the policymakers, on governments, and it's really not our problem, but I think that will not do. So why is this really so? And I would like to submit that it's basically because early warning systems are conceived in a top-down manner and tend to be hazard-centered, and therefore there's also a lot of fragmentation in the way in which we sort of do our analysis. So is it important to bridge the gap between top-down and bottom-up approaches? Certainly, and how would may we do that? So the first suggestion is that we ensure integration of all forecasts and observations with community monitoring and preparedness system. So is there an awareness within the scientific community about community processes, about indigenous technologies, about the fact that you are dealing with people who may probably not be educated? So I think there are questions there of integration and what is the effort that we need to make this integration possible. The second is paying adequate attention to lead time. I think this is something that has been flagged. So there needs to be enough time for operational decision making, both at national and local levels. I think we are doing well in terms of national levels, but local levels, big question mark, because of which we continue to have high levels of mortality. So better and direct linkages between technical capabilities with the local level through participatory approaches where community needs to define the rules that will be taken on board to develop the whole system. We develop a system from maybe a space which is not necessarily linked to the community. We're talking really about working on bottom-up approaches. And then finally, of course, by ensuring commitment of governments to transboundary sharing of floods and information. This is a huge area of work, and I hope we are able to sort of do further work on this at an international level as well. This is my last slide, which offers the conceptual framework of early warning systems organized around 4 pillars offered by the UNISDR. The 4 pillars are risk knowledge, monitoring and warning, dissemination and communication, and response capacity. Now, very quickly, is this really possible, or is it just something that is imaginary? Now, very quickly, I'd like to flag the fact that in Moldova, you have seasonal campaigns to increase risk awareness. There are information booths, there are cultural activities which target vulnerable categories of people like women, children, and the disabled. Disabled is again a category we often sort of overlook. In Philippines, there are a number of interesting initiatives which help communities to understand weather information and interpret it properly in terms of what action needs to be taken. There are several platforms such as mobile apps, web pages, several forms of social media. In the Hindu Kush Himalayan region, there is again very interesting flood risk management, local early warning systems that are being experimented with. Cuba has done phenomenally well in terms of developing civil defense modules that are mandatory in all programs of higher education systems, and issuing warnings in specific languages and dialects. I think this is something that's important. So customizing solutions based on identified needs of the community. Community radio stations in Uttarakhand is doing extremely well. So there is, of course,
I think Professor Janki, we are left with only 7 minutes for the whole session. So I think I will request you quickly conclude it, and after that immediately Mr. KJ Ramesh also can give his quick overview on the communication part.
I was actually on my last sentence.
Please.
The point I'm making really here is that we need to recognize that all of this is human resource intensive and requires commitment at the highest levels if lives are to be saved, because we talk of saving lives and do more technology, but less in terms of outreach. So it's a matter of according the priority that it deserves. Thank you very much.
Dr. Ramesh.
Thank you. Thank you. Having realized the importance of creating a basis for action through an effective communication system, we need to generate first important factor is for doing that is the floodplain mapping of the inundation. Coming out of the hydrodynamic models, and then we can know the extent of inundation and areas of inundation and depth of inundation. With frequent updation, we will have the duration of inundation. So having got all this with the lead time information using the observed data and the forecast data, you will have at least 48 hours lead time inundation scenario. Then that is a good time for sending the customized information to the different kinds of responders. Government is the first responder, community is the second level responder, and the response agencies, NGOs, relief agencies are the third level responders. So whatever kind of information is required to those different kinds of responders, that information got to be customized and disseminated to them at the quickest possible time by multiple sources of communication. Now we have a different source of communication information. We will have a fail-safe means of communicating them for planning effective response, and vulnerable people got to be moved to safer areas, to relief camps, etc. by a organized relief effort based on the warning system and inundation maps, etc. Now we have to integrate all this to see that mortalities and morbidities related with floods will get reduced in course of time. We have so much of knowledge discussed about it, and we should make all this knowledge become possible for effective response and minimizing the impact.
Thank you. Thank you, Dr. Ramesh. We are touching, I think, 51 minutes. So we have the 4 minutes in hand. So now what we are doing, actually I noted, one of the comment, one of the suggestions made by you, made by Mr. Panda and our other panel experts, including Professor Janki. We have to give attention for the lead time. If we have a very good lead time for our forecasting, for our communication, so everybody is well prepared. Otherwise, if you are telling me today that tomorrow it will happen, but if you can tell me with a lead time 3-4 days, certainly it is going to be very helpful for the society and for the communities. So coming up, now we are reaching to the stage of the session that we have to summarize this. As you know that we are putting all components, all pieces together, let it be modeling, data, communication, all together. So what we have observed that really input of the reliability and accuracy of the rainfall data for any kind of the flood modeling is very important. And if we can give IMD is doing a fantastic job in this one. WMO is also doing a good work with the support of all the nations. It's a very good important, and we have to work on that. And as our panelists explained, and I also personally feel that high resolution DEM is very much required for any kind of the inundation modeling. Otherwise, our models, our outputs cannot be accurate. The extensive use as suggested by Rohini as well as Mr. Michael is also very important component for the flood modeling. The best use of remote sensing, satellite information, and the geospatial techniques is very much required for in the flood forecasting. And has to be now, the time is coming that the models are to be, web-based. They are running automatically without minimum, without any kind of the intervention from the public or from the man. So that is also one of the point. And the reliable and fast communication, as you and the Professor Rohini indicated, it's very much required. Otherwise, the use of our flood outputs, will not help to anybody if they are not communicated. The people are living at such a locations that, they are badly affected under the flood events. The response to the warning and the preparedness to the society is also very, very important. Our agencies are to be, at a same pace to take the actions to reduce the losses, to save the lives. So this was, about our session. I'm really thankful to all the panelists, experts to tell us, they are telling us, where the flood will come, when the flood will come, how much the flood will come, how it will be communicated to the society and to the vulnerable communities. It's very, very useful information we shared with all the audiences on this UR20 platform. I'm thankful to all. And which is with us is next slide, Lakshman. If somebody wants to write us, to communicate us with the panel experts or with me or with RMSI, so this is the information available for them. So again, I would like to thank to all, Mr. Panda, Mr. Ramesh, Mr. B.P. Yadav, Professor Janki, Rohini, and Michael, along with my session manager, Lakshman, he's working in the background. You can see how smoothly our session went. This is also time management. And right now, just to inform you, we are just on 55 minutes. That was our time allotted for this community session. Thank you all and have a nice time. Okay, thank you very much.